Yeah, and I was reading an article in The Economist that talked about Bertha at the University of Bristol. So, as a Formula One enthusiast, I was fascinated to read about composites reshaping the future of manufacturing high performance machines. But I wasn't sure when Nissan would sell a car made from high performance composites in the showroom for the average buyer. So, do these cool materials become available for common applications anytime soon?
Oh yeah, yeah, definitely. I think at least glass fiber reinforced polymers have been used for decades in cars. It's just you don't necessarily see it. Uh, Carbon fibers are more, let's say, marketable. It's the cool word these days. Well, these days it's been for a while, but and it looks good. So it looks nice on the car. You can see the pattern. So it's used a lot for, well, of course, for because it's lightweight and it's strong, but also it looks good. So it's a point, I'd say it's a selling point with some people. But definitely, in terms of cars, yes, there are definitely some cars that are already use those, well, composite materials. So the price point varies. Glass fiber is going to be more accessible, more affordable. But yeah, carbon fibers were getting there in the automotive industry. But we also see them for sports equipment. So this is more readily accessible, I would say, at more affordable in the sports industry. If we talk about, common products
Yeah.
that regular people can have access to.
Hmm. So composites are magical and they kind of remind me of Captain America shield. I don't know if you know about it,
Yeah.
but if you believe Stanley, the shield is made out of vibranium, which is the hardest material available to humans. So can you please tell us about how carbon is at the heart of composites? And like I can see in your research, joining of composites is not as easy as welding it together. So can you share a bit about challenges about manufacturing composites and then crafting parts from it?
Yes. Um, yeah, okay, I have to think about it, this one, but um, yeah, so there's a multitude of manufacturing methods that are available to for composite materials. And that's where, I mean, depending on the type of polymer that you use, you have different manufacturing methods that can be used. And generally, you have two main categories, thermoset polymers and thermoplastics. Just going to quickly explain thermoset. It's, well, you probably know epoxy glue. It's like glue. So basically over time, it's going to solidify. And once it's solid, you can't reprocess it. So you can't melt it again. Thermoplastics are like any common plastics that you have access to. Okay, I don't have any, but like plastic bottles. So if you heat them up, they're going to melt, and then when they cool down, they solidify again. There are other classes of polymers. I just don't want to exclude like the newer polymers like vitrimers that are emerging, in the past few years, that are actually thermosets, but they can also be melted. But generally, right now in the larger industries, automotive, aerospace, um, people are going to use mostly, epoxies and other type of thermosets and some thermoplastics as well. So they both have advantages, disadvantages. Um, so thermoset typically will be easier to manufacture. So you have, well, when I say easier, I mean you need lower temperatures to process them. So it can be more energy efficient, again, depending on the manufacturing method that is used. While thermoplastics will usually require higher temperatures. And that's a bit one of the, I'd say not necessarily largest issues, but that's one problem where industries try to incorporate thermoplastic composites in their applications, and they have to change their equipment so that it's suitable for thermoplastic composites. So there's a little bit of resistance there. But overall, so they both have pros and cons. So of course, thermoplastic composites, as they can be melted, you can join them by using welding. So basically you melt them wherever you want to join them, you melt them locally, and then when it cools down, they will be solidified. Um, I think, and then some issues with the manufacturing process themselves is that we always want to minimize defects. So because you have basically a polymer that's going to be in a liquid form, you know, high viscosity at some point during the manufacturing process, you can always have air that's going to be entrapped. So you will have voids, you can have fiber deformations, and then this will have an effect on the final performance of your component. So it may change the mechanical properties. So those are some of the, I'd say, main challenges. And if we talk about, again, automation of the manufacturing processes, then it's related to how you position your plies and your fibers, and if they're aligned correctly, or if you have gaps between your uh, layers, then you may introduce defects into your components. So there's a lot of work as well done on non-destructive evaluation of the quality of composite materials. So right after manufacturing, we want to see, do we have voids? Do we have defects in the part? So you can already estimate, well, if you need to modify the manufacturing process, or if you need, well, to make changes in order to improve the quality. Um, I think, yeah, that summarizes the answer.
And back to Miss Corina, I believe that we know less about the ocean surface than we know about Mars. I also saw that there are many companies, especially in Europe, that are working on creating autonomous marine robots. So, can you tell us about the specific challenges that your team has faced?
Yeah, so it's true. That's what scientists say. We know less about the ocean that we know about the outer space. And for example, we know that we mapped the ocean only 5% at a meter resolution. So we know very little. And the challenges actually are, well, the environment itself. It's a very difficult environment to work in, because when you design robots that are supposed to go in the water, you want to be sure that there are no water leaks. You don't want to destroy your robot. So that is one. Then it's pressure, like the pressure that those robots have to operate. Like the deeper that you go, the pressure makes a huge difference. So the materials used to make these robots that they go in the deep depths of the ocean, they are very expensive. So that increases the price of the robots. Then there's the communication problem. As I said before, there's like no GPS, there's no Wi-Fi. So you, especially if it's an autonomous robot, you drop it in the water and you are not sure where it is. You just hope it will come back to you. So all of this makes this environment challenging, but also the limited batteries that robots can carry, the autonomous ones as well. um, and then if we are talking about remotely operated vehicles, that they need a cable to be attached to a surface vessel where it's like the command room, and then you will need a large vessel to deploy that robot. You will need like really good human operators to maneuver the robot. So that's why we know so little. It's difficult because it's expensive to create robots that are going and they are able to survey those type of environments. Specifically, so my group it's working on trying to enable autonomy for these underwater robots, but also more into the area of not only surveying the environment but also interacting with the environment. So now you want to collect samples from the ocean. You want to have these autonomous robots with a robotic manipulator that are able to fix or like maintain offshore oil and gas platforms, or maybe you want to do some geological sample, collect some rocks. So you would like my group specifically looks in how do we do these processes autonomous. So now you don't have one single type of robot that you are sending there. You have like two robots put together that they have to collaborate, and they have to be robust. So what we encounter as difficulties is like, how do we manage or to make these robots to be stable and behave as expected? It's a problem of precision. We want to be as precise as possible. So when a wave comes or like the strong currents, we don't want our robots to be knocked out from the environment that it's working on or it's attached to. Um, and then again, like just a simple fault in our robot can be disastrous, can actually lead to losing the robot and not coming back to the surface. Or it can lose all the data that it has collected, and have been a lot of cases when this has happened. For big institutions, they lost robots, they lost large amount of data. We had like last year, for a day, we sent a robot in the water to collect some data. It said it came back. We went to pick it up with a boat, and when we went there, the robot was not there. So what do? You start and look, and like everything that you see is just water around it. So we looked basically for a day before being able to find it, and we found it just because we had a really good like boat captain that managed to figure things out. So those are the challenges of working with robotics underwater. But it is an area that it's increasing lately. So there are a lot of companies in Europe, in the US, that are focusing on designing more autonomous robots, and increasing the market, because it is a market. There are a lot of, so military use autonomous robots, underwater autonomous robots. Oil and gas companies, they are interested in such system. And then scientists, like small, like marine scientists, biologists, ecologists, they would need this type of systems. The problem for scientists is that, as I said, these robots are very expensive. So another interesting area is like, how do we make them more affordable? How do we drop the cost of manufacturing this type of robots?
Yeah.
Wow.
So you listed a lot of issues. So how have you worked on resolving these issues?
So that's a very good question. So some of them, they are still unresolved. So my group is specifically focusing how do we design this control and planning algorithms. So we are focused not on the communication problems, but like how do we make them robust and stable. So what we do, we look at different algorithms and different methods that they are adaptive. So they can learn from the environment where the robot is working, like have some sensors, and then adapt the behavior of the robot on the spot, trying to improve the performance. That's the main issue. So we are always studying in the environment. So it's a lot of AI algorithms, but also like more classical methods that can be leveraged. So it's mostly through software improvements, and then these in terms of improving the accuracy, the robustness, and not being knocked over by the currents. In terms of hardware, it's just a continuous process of reiteration. So the way how we start is we start testing what we build in small tanks with 3-4 people looking if there's any water leaks, and then as soon as we see it, we take it out, we repair, we find where the leak is, and we always go like incremental. So we won't just test our robot at 100 meters. We say, okay, we start in a tank, then we go like in very shallow waters, like 1 meter depth, like in a lake somewhere. That works. Okay, let's put it at 2 meters. Does it work there? And so on. So everything has to be done incremental to be sure everything works as expected.
Yeah. And why is Louisiana State University at the heart of so much research in this area for both you and Miss Palardy?
Um, So in terms of like underwater robotics, and my interest is just the location. It's very favorable. We are really close to the Gulf of Mexico. We are close to, well, we have Mississippi River that's passing through Baton Rouge. So all this environment makes it extremely good for my kind of research. Also, the school has a really big College of Coastal and Oceanographic Sciences. So we can collaborate with them, and they are scientists like marine biologists, ecologists, and they tell us, okay, these are the problems that we face. And us, like the mechanical engineering, we can come up with solutions for their problems. So I think that was attractive to me at the university and what offers in this location. Um,
Yeah, for composite materials, there are also some industries, mostly in the New Orleans area. Lockheed Martin, LM Wind Power, which recently moved there. And there's a NASA Michoud assembly facility as well. So they do research on, they do research. They work, research and development on composite materials. And there's also the NASA Johnson Space Center in Houston. So there's like some, I don't know, nice opportunities specifically in that field for research and more development.
Yeah.
I think that's one reason why, there's materials research. Yeah.
And as we said before, it's collaboration. You can't work alone.
Yeah.
You need a good support group. It's teamwork.
And both of your work is so fascinating, and I'm sure a lot of high school students across the world would love the opportunity to get a chance to work in your labs. So, what advice would you give them, and how best should they prepare themselves?
How to think
Well,
about it. Yeah,
I
you can.
think it's important. So my advice for them would be, you need to find out what you like. Like you need to do something that you really like. Research can be challenging, but if you do something that you think you would really, really like, then it's all worth it. So if you think you would like the area of robotics, I would say learn like mathematics. It's really important. Physics is important. Informatics, like computer programming, it's a big part. So I would say take some courses in this, do some independent studies, and always like try reading about new robotic system. There are a few resources out there that I can share, like if you need, about this area. So generally what we are looking at, what I am looking for when students are want to work with me would be, okay, do you really like this area? If you think you really like it, then yes. Are you motivated? Like trying to develop new stuff? Those are the questions that I generally ask students that want to work with me. Um, Research and working in these labs, it's very rewarding, but it can be also very demanding. So you need to be sure that you like what you are doing to be happy.
Yeah.
So I would say that would be my advice to high school students, like work in areas that you really like.
And what
Yes.
about you, Miss?
Sorry, I was going to add to this. I think figuring out what you like is one of the most important, probably the most important step. And sometimes, yes, it's difficult. You can read about it, but then when you go in the lab, you can realize, I don't really like this type of work. And there's also different types of, research groups where some of them are more applied in terms of, more practical. So where you're actually going to work in a lab and then do, in my case, mostly manufacturing. You test mechanically the components, you break stuff. And then some others are more about computer-based research. So you can do simulations, you can do programming. So you also want to try to figure out what type of research work you prefer. So if you're more an experimentalist or more computational, or a combination of both as well. But I think, yeah, definitely if you don't like if you don't like the field that you end up choosing for grad school, or research in general, it's going to be very painful and not let's say not productive in general. So that should be the first step, figuring out what you like the most.
Also, I think after high school, when you go to college, like to university, as an undergraduate, you might have the possibility to join different labs. And
Yeah.
maybe that's what students should do, like go and work for a few weeks in different labs, like reach out to professors and see what part of research do they like, what area do they find more interesting. So experiment before deciding exactly, okay, I want to work in this
Mhm.
field. See how other people work, because sometimes you might like the area, but sometimes you might not get along with your professor. Maybe you have like different, not necessarily not get along, but you might view things in a different way. So that's perfectly fine as
Yeah.
well. So you need to explore.
Yeah. Well, we could go on and on, but I'm mindful of your busy schedule, and I'd like to sincerely thank you for taking the time off and speaking with me over a weekend. And if anyone wants to check out more about what they do, the link for their websites will be in the description. And I wish you all the best in this collaboration and in all your research work. And thank you.
Thank you
Thank
very
you so
much.
much.
Hope you learned something.